Welcome to Mkown, episode 1. That's how I'm gonna call this series, and we are basically going to be reinventing the wheel for learning purposes. I'm gonna be writing programs that you take for granted that they exist, like databases, compilers, HTTP servers, network protocols, you name it. I'm gonna be writing those programs from scratch and walking you through the process of how you can go from knowing almost nothing about these topics to basically writing a toy project. I've done this a couple times before. I wrote a memory allocator once. I also wrote a reverse proxy HTTP server. So I kind of learned how to approach this type of projects. Okay, so back to the database thing. Here's my current limited understanding of how databases work internally. Let's take MySQL, for example. When you create a database using MySQL, what happens is that MySQL itself, the program, creates a folder for that database, which you can see here at this location. Now, when you create a table inside of that database, what happens is that MySQL, or rather the storage engine that's used internally, creates a file inside of the database folder, which you can see here. That's the user's file. This file contains two things. First, the table data. If I insert rows into this table, all this data is going to be stored in here. And then additionally, this file also stores an index for the primary key in this case, which you need because you have to be able to search by primary key fast. Like you can't do that linearly, one by one, row by row. And I know that this index internally is built using some esoteric data structure called BTree or B+tree. They're not even the same thing, they're different, but it doesn't matter. The thing is that this data structure can be somehow stored on disk, and it speeds up primary key lookup in this case, or any other field if you index that field. This data structure can also be modified through main memory or RAM, although it's persisted on disk. But I don't know how any of that works. How do you implement a BTree? I have no idea. How do you store that on disk? I don't know. Which means I need to do more research. And so phase 1 of this project begins. Okay, so I've done some research. I still haven't figured everything out yet, but I think I know just enough to get started. Let's try to implement a database without using BTrees and see why they're necessary. So imagine we want to store some user data. Let's say that for each user, we need to know their unique ID, which is also going to be the primary key, and we also need to know their full name. So we have a table with 2 columns, and then we can have as many rows as necessary. This is basically a spreadsheet. Okay, now remember that a database table is stored in a file, right? How can we store this spreadsheet-like data in a file? Well, we could use the CSV format and insert what's called a delimiter between each column and also between each row, but this is going to complicate things because I can't jump from one row to another immediately. I'd have to find where the row delimiter is instead, and by find, I mean search for it linearly, byte by byte, until one of the bytes matches. Since this would be extremely inefficient, we're gonna get rid of delimiters and make all the rows the same size. The username has variable length, so we need to force strings to have a maximum number of characters. For example, 255. If the username can contain at most 255 characters, I'm gonna need 255 bytes to store the string itself, assuming ASCII encoding, of course. And then I'm also gonna need 1 byte to store the length of the string. That's because 1 byte is made of 8 bits, and with 8 bits you can count up to 255. That's why everybody uses 255 as the maximum character capacity for short strings such as names and emails, by the way, because if you use 256 or more, you're gonna need 2 bytes per row instead of 1 to store the length of each string. So with that in mind, now we know the exact byte length of each row. The primary key is an integer, so that's going to be 4 bytes. Then the username is a string that needs 1 byte for the length and 255 bytes for the maximum character capacity, which means that each row is going to be 260 bytes in total. So now let's say I receive a query asking for the user with ID 50. If I'm searching linearly, I can read the first primary key in the file. If the key doesn't match, skip 260 bytes, read the second primary key. If the key doesn't match, skip 260 bytes again, read the next primary key, and so on and so forth until I find the key that matches. This is better than the CSV approach, but the problem is that I'm still searching linearly, O of n, right? If I have 50,000 rows, this is going to be an issue because reading from the disk is much slower than reading from memory, and even more so if you have to do it thousands of times. And that's why we need to index the primary key. An index is going to allow us to search in logarithmic time, O of log n, which is much more efficient than O of n, especially as the data grows. We said that we're not going to use BTrees just yet, so let's try to use a normal binary tree for the index and see what happens. I'm going to skip the binary tree explanation. Let's just assume everybody knows how they work. This is basically data structures 101. So let's suppose we have a file with the table data stored in the format we've discussed before, and we want to find the row that holds primary key 8. Keep in mind that this row could be located anywhere in the file, because primary keys don't necessarily have to be integers that increment by 1, as in this example. You can't just jump to row number 7, it's not that easy. If we want to find that row faster than O of n, we could store a balanced binary tree somewhere, in memory for example, where each node holds a primary key value and also a pointer to the row where that primary key is located, or in other words, the row number. If we had that and we wanted to find primary key number 8, we could traverse the binary tree until we find the key we're looking for. And then once we have that, we also know the row number, so we can just jump straight to that row in the file, because all the rows are the same size, so we can just multiply. This binary tree approach has a couple problems. First of all, normal binary trees are not balanced by default. If our primary key is actually an integer that increments by 1, and we keep inserting keys into the tree in ascending order, we'll end up with a linked list instead of a tree, so we've solved nothing. Our worst case search time complexity is still O of n. The second problem of binary trees is that it's not easy to store them on disk. Think about it, how do you even store a binary tree in a file? And you must do it, of course, because you have to persist the index. And also keep in mind that if the index is big enough, if you have hundreds of millions of rows or terabytes of data, the index itself could be gigabytes in size, so it might not even fit into main memory. You might not even be able to load the entire tree into memory. You'd have to load it one chunk at a time somehow. Okay, so this seems pretty complicated, but BTrees solve both of these problems. Here's a BTree. You can see that its structure is somewhat similar to normal binary trees in the sense that smaller keys are kept to the left while larger keys are kept to the right. The difference is that each node can have more than 2 children and each node can hold multiple keys. How many of them? Well, to answer that, we need to define the minimum number of children per node. Let's call that number C and let's make it equal to 2. Once we have that number, we can compute the rest of properties using some simple formulas. These properties apply mostly to internal nodes, because the root node and leaf nodes are exceptions. But the reason you need to keep track of these properties is because BTrees are self-balancing. They always stay balanced no matter how you insert the keys. The self-balancing algorithm is pretty complicated, so I'll try to summarize it as simply as I can. Before we start, from all the properties that you see here, the one you need to remember for now is the maximum number of keys, which is 3 in this case. Alright, so let's try to insert 10 keys in ascending order into the BTree and see what happens. First of all, we create the root node of the tree and we start inserting keys into that node in ascending order as if it was a sorted array. And we do that until we reach the maximum number of keys. Once that happens, further insertions will cause the tree to self-balance. Here's how it works. Key number 4 cannot be inserted into the root node because the root node has already reached the maximum number of keys. So we take the median key, which is 2 in this case, because 1, 2, 3, 2 is in the middle. So take the median key and move it into the parent node. Since there is no parent node because we're already at the root of the tree, we're gonna have to create a new node. That node will become the new root of the tree, and then we're gonna split the old root into 2 different nodes. The first one containing the keys before the median, and the second one containing the keys after the median. Finally, insert key number 4 into the rightmost node in ascending order. That's the general description of the self-balancing and insertion algorithm. I'm gonna let the animation play until we insert all of the remaining keys, but basically there's only a couple things you need to do. First, find the node where the new key should be inserted. If that node has already reached the maximum number of keys, then move the median into the parent. And after that, split the node into two different nodes. This algorithm is recursive, so it becomes more and more complicated as the tree height grows, because at some point you're going to have to split multiple nodes, you're going to have to move multiple keys upwards, and also the root is a special case because it doesn't have a parent, so you have to create a new root and all of that. But that's how you ensure that the BTree stays balanced. And as such, searching is always O of log n. It never becomes a linked list where searching is O of n. That solves the balancing problem. Now, how do we store this BTree in a file? Before I explain that, one last thing you need to know about storage is that when you read from the disk, you can't read 1 byte at a time, or 2 bytes at a time, or 5 bytes at a time. You have to read in blocks. Blocks of size 512 bytes or 4096 bytes. It depends on the physical disk itself, on the drivers, on the operating system, and a bunch of lower level layers in between, but that's not important. What's important is that we can take advantage of this to minimize disk reading operations. The way we're going to store the BTree is we're going to figure out how many keys and children pointers we can fit into one block. For example, let's say that we can fit 100 keys. Okay, then each BTree node is going to have 100 as the maximum number of keys, and then we're going to store each BTree node into one single block. If the block size is 4 KB, not kilobytes, I'm talking about 4096 bytes, if that's the block size, you can imagine a file where the first 4 KB store the root node. The next 4 KB store a child of the root node. The next 4 KB store another child of the root node. The next 4 KB store a child of one of the internal nodes, and so on and so forth. So we can read this tree one node at a time, with one disk operation at a time. It could be gigabytes in size and it doesn't matter. Also, how does a node point to its children? Well, children pointers are basically block numbers. We start counting blocks at 0, and then we can point to any of them and jump to any of them in the file by multiplying. I'm not sure how all of this node splitting business is going to work in a file, and I'm also skipping a lot of details, but keep in mind I'm explaining all this stuff as I'm learning myself, so a lot of things may be wrong here. Take everything I say with a grain of salt. Last thing before I start writing code. What exactly am I going to write? Well, we're going to have a storage engine that's going to take care of all the BTrees and blocks and all of that business. Then we're going to have an SQL parser, or SQL, or SQL, however you want to call it. And this component is basically going to take in statements like create tables, select, and turn them into some sort of data structure that the storage engine can understand. Finally, we're going to expose this service through TCP. I'm not sure if I'm going to use async or a thread pool, I don't know that yet. We'll also need to deal with concurrency and multiple connections updating the same rows and all of that. I guess that's just a mutex, but we'll see. Optionally, we could also implement a caching mechanism to keep BTree nodes in main memory to speed up searching, but I'm not sure if I'm going to do that in this video because caching is hard and I have to deal with enough hard stuff anyway. Implementing all of this is going to take a lot of time, so I'll get back to you when I'm done. Phase 2 starts now. So after 7 months, 251 commits, and 25,000 lines, I finally have something basic that I can show you in practice. So I'm gonna do a quick demo and then I'll explain how the internals of the database work. First things first, I can create tables, of course. Then I can also create unique indexes, either manually or automatically. And in order to keep track of all these relations, there's a special table called mkdb meta. So when I had to implement this, I was like, hold on a second. How can I create tables if I already need to be able to create tables in order to create tables? That's how you know you're in deep computer science territory, when everything becomes so recursive that you're starting to question your own existence. Now, these indexes, of course, are not there for no reason at all. The program actually makes use of them. So if I send a query like this one that searches by email, you're going to see that the program makes use of the email index to get all the rows. And it's also going to decompose this expression into multiple parts depending on where they need to be evaluated. So this is a query plan. I'll explain later how that works. Now, moving on, I can also do all the CRUD operations. So I can insert data, I can also select data, I can update data. So there's the update. And finally, I can delete rows. So after this, there should be only one row left. That's everything in terms of CRUD. But I can also do sorting, which you might think it's easy, but it's actually not at all. Mainly because the results of the query might not fit in RAM. And that's one of the constant problems that you face when developing a database, is that you can never assume that something fits in RAM, because 100 million rows will not fit in there. So you gotta sort on disk. And also the reason I'm showing you all these weird expressions is because SQL has to actually be able to execute any random expression that you throw at it, which is something that I didn't even think about until I actually had to build the parser and the virtual machine that runs all this. And I find it interesting because one of the projects I had in mind was writing my own compiler or interpreter, but with this, I'm already halfway through. Moreover, we have all the transaction business, so I can start a transaction, I can apply some changes to this table, and now I can decide whether I want to commit, which means that all these changes will be written to disk, or roll back, which is going to reverse all these changes even if they were written to disk. Because you don't actually know when that happens. It's kind of hard to know due to how the system works internally with caching and stuff. Rollback is extremely important for databases because this is also related to crash recovery. So for example, what happens if the client is in the middle of a transaction? The client applies some changes to some table, and before the client gets to commit or roll back, the database server crashes. The power goes out or something like that happens, the server is down. So what should happen to these changes? Because the client didn't commit, didn't do anything, and the database is down. Well, when the database server gets back up, it must revert all the changes and go back to the state it was in before the transaction started. So if the client reconnects again and attempts to read the data is in the exact same state it was before the transaction. Finally, there's the whole multi-threading part, which I didn't put much effort into because I said, you know what, I'm not spending another 7 months on this project, so I just threw everything behind a mutex and called it a day. So basically, we can have multiple connections at the same time and they all work simultaneously, but there can only be one transaction at the same time. So if this one here starts a transaction, the other one will have to block on the mutex until this transaction ends. So let's insert some data here and let's commit. And once this transaction ends, the other one can go through, but there can only be one at a time. And in case you didn't know, if you don't start a transaction manually, each statement by itself is a transaction. So that's my database. In terms of functionality, it's extremely basic. You can only work with one table at a time. There are no foreign keys, no joins, no group by, no subqueries. So it's pretty simple, but in terms of how it works, it's not simple at all, which is interesting because in the beginning I wanted to do something trivial. I wanted to force all the rows to have the same size, but I didn't because even for a toy database, that would waste a lot of space, especially with strings. And so just to be clear, a serious production database will not allocate 255 bytes for every single string because that would waste a lot of space. It will only allocate what's necessary to allocate for each string. So what's the problem with that? The problem is that now you don't know what size each row is going to be. Now you're dealing with variable length data. And this introduces so much complexity that I had to spend half a year coding the solution for this. Now, of course, my database is by no means a production database, but it does work with variable length data. Let's start with the basics. How are we going to store our database on the file system? Because there are multiple approaches. The most logical approach, I guess, is what Postgres does. They basically store every table and index in a separate file, and then they have one directory for each database. So they keep everything organized that way. On the opposite side of the spectrum, we find SQLite, which stores all the information about a database in a single file. So all the tables and all the indexes in one single file. But in terms of I/O performance, it doesn't really matter how you structure your database. It doesn't matter whether you have a giant single file or 10 smaller files. You still have to spin the disk in order to read them. So you won't actually see much of a difference in that regard. If you want to improve I/O performance, you have to do sequential I/O, so reading or writing one block after the other, instead of random I/O. Random I/O is bad even with SSDs that don't actually have to spin, so you still need to favor sequential I/O. That being said, my database, MKDB, works just like SQLite. It uses a single file to store all the tables and all the indexes. We've talked earlier about how you have to read in blocks when reading from the disk, but we don't want to be limited to the block size, so we're going to introduce our own storage unit called a page. So a page is made of one or many blocks, and we are the ones who define its size. So we can have 8 KB pages, we can have 16K pages, 64K pages, or any other power of 2 in that range. Now in my case, I usually set the page size to 4K. So the database file is a sequence of 4K pages, one after the other. There are multiple types of pages, but let's focus for now on BTree pages, since those are the most important. From now on, BTree page and BTree node are synonyms that we can use interchangeably, and BTree pages point to their children using page numbers instead of block numbers. It's the same concept, but with pages. So each BTree page is something called a slotted page. Slotted pages allow you to store and organize variable length data more efficiently. Because if I simply stored variable records in the page one after the other as if it was an array, first of all, I can't easily do a binary search on them because there are no fixed indexes. I don't know where to jump, and I need the binary search in order to maintain the log of n. The second problem is that sorting is expensive. So imagine I'm storing variable records with keys 10, 20, 40 and 50 in this page. And now all of a sudden I need to insert the record with key 30. Well, I'd have to move a bunch of bytes towards the end of the page to make space for the new record and maintain ascending order. Doing that over and over again is pretty much unacceptable, especially when the page size is big. So slotted pages, what they do is they say, you want to insert a variable length record here, we'll put it at the end of the page. And at the beginning, we're going to store a pointer or offset to the record. Want to insert a new record, again, put it at the end of the page, and at the beginning we store a pointer. And we keep doing this over and over again. So the pointers at the beginning are called a slot array, and this array grows towards the right. The variable records at the end are called cells, although you can call them however you want, and they grow towards the left. So when the cells meet with the slot array, the page is considered full. The slot array offers many performance advantages. First of all, if I want to do a binary search, I'm going to do it on the slot array because now I have fixed indexes, so I know where to jump. Then if I want to insert a new cell, maintaining ascending order, I don't have to move the rest of cells. I can just insert the cell normally and then shift the slot array, which is way cheaper than shifting the variable length cells, because each pointer in the slot array is only 2 bytes. The maximum page size is 64K, so you don't need more than 2 bytes to store each offset. Now, we said that this is a BTree page, so where are we going to store children pointers? Well, each cell will have a header where we're going to store a page pointer or a page number. And these page numbers must also be ordered. So for example, if I follow the pointer in the cell that stores key 50, I know for a fact that all the cells in the new page will contain keys that are less than 50 and greater than 40, which is the previous key in the current page. And that's what allows me to traverse the BTree in an ordered manner. So how do we store rows? In terms of how the row looks like, it's basically the same format I showed you in the beginning, where columns are stored one after the other in binary format. The only difference is that now strings are not wasting any space. So if a string only needs 5 bytes, I'm only using 5 bytes. And I'm also using UTF-8 instead of ASCII. So we gotta be smarter about how we store the length, but not important. The more important question is, where are we going to store rows? How are we going to store the tables, right? And we also have to point to rows from external BTree indexes. So how do we do this? Well, there are 2 main formats. Again, going back to Postgres and keeping it extremely simple, they have a table file that stores rows in slotted pages. This is not a BTree, it's just pages, one after the other, sequentially. And so each cell is a row. And each row has a location defined by its page number and its slot index in the slot array. That's why they use slotted pages. And so now, if you want to point to a row from an external BTree index, from the primary key index, for example, which would be a separate file for Postgres, you just have to store the primary key and the row location. And once you find the key, you also know where the row is. The problem with this approach is that now, in order to keep track of all the pages in the table file, you need something called a page directory, which is another file where each page stores metadata about pages in the table file, because you need to know exactly where to find free pages or free space, and you can't do that linearly, of course, because that's inefficient. So you basically need 3 different disk data structures. You need the BTree for indexes, you need the page directory, and you need the table file. But then there's another approach called index organized storage. This is what SQLite does. In this approach, we store tables as BTrees, sorted by the primary key. And so each cell in the BTree is a row. So when I found out about this, I was like, you're telling me that all the code that I wrote for indexes, I can reuse it to store tables, and I don't need to change anything, and I don't need more data structures? Then I'm definitely doing this. So I copied SQLite here. Now, this approach has a drawback, which is that we can't use the row location to point to rows from external BTree indexes, because the row location will change frequently due to the BTree balancing algorithm, which needs to keep everything sorted by primary key. So we need to use the primary key to point to rows from external indexes, from a unique email index, for example. This index would store the email and the primary key associated to that email. So we would find the email in log of n time, and then we would find the row in another log of n time. Whereas the previous approach skips the second log of n, because once it finds the email, it already has the row location. However, we have the added benefit that the primary key is not an external index for us. So queries searching by primary key will not have to read a BTree index first and then the table BTree. They straight up read the table BTree. It's like an automatic index on the primary key. That's why it's called index organized storage. There's only one piece missing. We said that pages are fixed size, 4 KB in this case. So what are we going to do with rows that require more space than that? Well, we're going to use something called Overflow Pages. Basically, when the size of a single row goes past a predefined threshold, like for example 1/4 of the page size, then we're going to split the payload into multiple chunks. The first chunk will be stored in a cell of the BTree page. The last 4 bytes of this cell will point to an overflow page that's going to store the next chunk. This overflow page will have a header that's going to point to the next overflow page, which is going to store the next chunk. And so now we have a linked list of overflow pages. Whenever we need to read the contents of this row, we have to sort of reassemble the entire thing into a continuous sequence of bytes. Putting it all together, the database file is a collection of table BTrees, index BTrees, and overflow pages. So you might think that this is a mess because everything's in the same file, but it's not, because the file is just a sequence of 4K pages one after the other, and we know where every single BTree is because each BTree has its own root page, and we have pointers to all the overflow pages. So everything's nice and tidy. Initially, this was my goal with this project. I wanted to understand how a database is structured. How do the individual bits and bytes look like in this mysterious database file? But once you have all these complicated disk storage data structures laid out, you gotta implement some sophisticated algorithms to work with them. So, BTrees yet again. The problem we have with BTrees now is that we're storing variable length cells in them. So all the formulas I show you in the beginning, they don't work anymore. Because how many keys will each BTree page have? Nobody knows, as many as you can fit basically. There's no upper bound, which of course makes things complicated. And there's another problem. The default balancing algorithm keeps pages only half full when inserting sequentially, because each time a node splits, the node at the left remains only half full, because you take the median, so you split in half, but then you insert into the right node. And so by the end, you will have a bunch of pages that are only half full, wasting space. So the balancing algorithm is actually one of the most complicated parts of the entire code base. I probably spent 2 months just on this, because now this algorithm is a giant recursive function that I copied from SQLite. Object-oriented gurus are going to hate me for this one, but hey, this is low-level systems programming. We don't do Java here. Explaining in detail how this works would take forever, but it's based on this simple idea. If we take a closer look at how insertion works, you realize, hold on a second, do I actually need to split a node every time it's full? Now I don't, because I can just sort of reorganize the keys around and delay node splitting while populating sibling nodes. I can do that until there is no more space left, and then I split and repeat again. This algorithm does exactly that, but with variable length data. So now that we have a working storage engine, the user will send us SQL, right? Which is basically a string. So how do we go from a string to running BTree algorithms on disk? Well, first of all, we gotta parse the string. I'm not gonna talk much about parsing in this video, even though I wrote a lot of code just for parsing alone, but I don't think it's that relevant to databases, so topic for another video. Here I am basically going to speedrun parsing. Step 1, you need something called a tokenizer, which takes characters as inputs and outputs token types. Step 2, now you gotta feed these tokens to the actual parser, which is going to produce something called an abstract syntax tree. This tree represents the entire SQL statement in this case. As I said, I'm gonna keep things simple, but if you're interested in parsing, I use something called top-down operator precedence parsing, which is an algorithm that came out in the 1970s, and it makes it pretty easy to write parsers, because the biggest problem is knowing when to execute an operation inside of a larger expression, and that depends on the operator. And so this type of parsing consists of a couple of mutually recursive functions that keep calling each other until they end up building an expression tree, and with that, the AST is complete. Then there's something called the analyzer, which basically does context-dependent analysis. So things like this table doesn't exist, this data type is wrong for this column, all that stuff is handled here. And then on top of that, there's the optimizer, which basically simplifies the SQL statement to avoid computing unnecessary operations over and over again, because this is not machine code running on the CPU, it runs on the interpreter, so it's pretty expensive. So parsing, it looks complicated because of all this mutual recursion and stuff, but honestly, I have never written a serious parser like this one before, and still this was the easiest part of the entire codebase to write. Mainly because it's not low level, you're not dealing with bits and bytes, you keep everything high level, and if the language you're using supports pattern matching, this is a joy to write. You don't even have to think about it, you just write it, it writes itself. So now that we have a complete AST, just like a compiler would turn its AST into machine code that the CPU can run, we have to turn our AST into something that our storage engine virtual machine can run. So that's the query plan, which you saw earlier in the demo. The query plan is yet another tree. Man, computer science pretty much boils down to pointers and trees. But anyway, the query plan tree represents all the steps needed to compute the results of a query. So a basic example would be select a couple columns from a table where some condition. The first step is scanning the table. So how are you going to scan? Are you going to use an index, multiple indexes, or you just do it sequentially? Then once you know how to scan, you have to filter the output based on the where condition. And finally, do something called a projection, which is the fancy relational algebra term for picking columns from a row. In relational algebra, rows are called tuples, so I'll also use that term because that's what I'm using throughout the code. What's interesting about plans is that I'm using something called the iterator model, which essentially what it does is it processes tuples one by one. So every node in the query plan tree is an iterator itself, an iterator over tuples. So when the top level plan is asked to return a tuple, we basically call .next on the plan. That node in turn calls .next on its child, which in turn calls .next on its child. At some point we're gonna get to the bottom of the tree where we're gonna find the scan plan or the scanner. The scanner has a cursor that goes over all the rows and returns tuples one by one without using any memory because the only state that it needs is the cursor. And that's what's interesting about this pattern. We can process a giant table one row at a time without worrying about RAM. Now, query plans are not the only way of doing this. Postgres does this, but SQLite, for example, generates some sort of bytecode and then they run that. It's the same thing, but I thought plan trees would be easier, so I copied Postgres here. So thanks to Postgres and SQLite because they carried me through the entire database development journey. I would not have been able to write all this code without Postgres and SQLite. And yes, I know the correct pronunciation is SQLite.
So, what is SQLite?
But it's kind of annoying to say SQL all the time at this point. I also use the lectures from CMU Intro to Database Systems. They're very well done and they're available on YouTube for free. So that's pretty much all I needed to write my own database. Moving on, what happens with algorithms that need to work with the entire dataset, like for example sorting? Well, there's a special kind of plan, which is the collect plan, that basically has a fixed size in-memory buffer where it stores tuples coming from the source, and once the buffer is full, it writes it to a temporary file. So it collects all the tuples into a temporary file. Now, if the rows can actually fit in the memory buffer, then everything is drastically easier. You want to sort them, you can just call .sort on the array and you're done. But when stuff doesn't fit in memory, that's when you gotta work with files on disk instead. So how do we sort a giant file of unsorted tuples? There's an algorithm called K-way external merge sort. I'll make an entire video on that algorithm alone because it's very complex, but in a nutshell, this algorithm divides the file into fixed size pages and it does a number of passes through the file until it's fully sorted. The algorithm has k input buffers for reading pages and one output buffer for writing pages. Let's say k equals 2. In that case, pass 0 would do something called 2-page runs. Each run produces a sequence of 2 pages that are fully sorted from start to end. Then pass 1 is able to do 4-page runs. Pass 2, 8-page runs. Pass 3, 16-page runs, and so on. It keeps multiplying by k, so it scales logarithmically, which is pretty awesome because if you have 5 buffers instead of 2, pass 0 does 5-page runs. Pass 1 does 25-page runs. Essentially, you're reducing the number of passes through the file, so less I/O, at the expense of using more RAM. And it does all this loading only k pages at a time in memory. It's not gonna load 25 pages because it only has 5 buffers, and that's the complicated part. When I implemented this algorithm, even though I know exactly how dumb I am, I felt like a genius because I was like, damn, this algorithm all of a sudden can sort terabytes of data and it won't even flinch. This is another one of those giant functions that will make OOP gurus mad, and this time I implemented it iteratively instead of recursively, so it has like 3 nested loops. It's like while, for. I don't know, it's awesome. And what you have to understand is that every single algorithm that works with large datasets, like aggregation algorithms, join algorithms, they all need to take into account the fact that the underlying data might not fit in RAM. And so they all have to be able to operate on disk, which as you can see is anything but easy. Even though I'm talking about caching now, it's actually one of the first things I implemented after the BTree. Caching is another one of those famous computer science problems, right? But luckily there's a simple solution. The simplest replacement algorithm I found is the clock algorithm. So the cache is basically a circular array where we load pages from disk. Every page has a reference bit so that when somebody wants to read a page from the cache, we set its reference bit to 1. Every page also has a dirty bit, so when somebody wants to modify a page, we set both its reference and its dirty bit to 1, and that's how we know which pages we need to write back to disk. And then there's the clock replacement algorithm. When somebody wants to read a page that is not cached, we have to evict one of the cached pages. So the clock is yet another pointer whose mission is to find a page that is not currently referenced. If the page that it currently points to is referenced, then it resets its ref bit back to 0 and it moves to the next page. If that page is referenced, it resets its ref bit to 0 and it moves to the next page. Once we find a page that is not referenced, we can replace it with one of the disk pages, considering that if the cached page was dirty, we would have to write it to disk first. So yeah, caching overall not that hard, but I did find some interesting bugs due to not writing exactly when needed and stuff like that, because you also want to be smart with this. You want to group writes of multiple pages together to do them sequentially and reduce I/O overhead. So how do we implement commit and rollback? The simplest solution I found is what SQLite used to do, which is something called the journal file. So the database is basically a bunch of pages. A transaction loads some pages into the cache and modifies them, so now you have a set of dirty pages. Essentially what you do is before modifying the pages, you write their original contents to a journal file. And then you can modify and safely write to disk. And so if you need to roll back, you just need to copy the original pages from the journal file back to the database file. And you're done, no more complications needed. If you want to commit instead, you just have to delete the journal file. It's that simple. This solution is good enough for a toy database that processes only one transaction at a time, but production-ready systems, they use something called the write-ahead log, which essentially keeps track of all the changes applied by each individual transaction. And also opens the door for multiple writers at the same time. You can start 2 transactions in MySQL or Postgres, and you'll verify that each transaction can see its own changes, but it can't see the changes of the other transaction until it commits. Of course, this is much more intricate. As I said in the beginning, this program would be a TCP server that accepts connections, and so I had to write my own little network protocol inspired by the Redis protocol, which I like because it's very simple, doesn't need fancy stuff, so I made something similar. Now, I'm not going to explain the entire format of each packet, it's all detailed in the documentation, but what's nice about this is that you don't have to use the console client that I wrote. You can write your own client, and you can write it in any language of your choice. That's what's nice about protocols. So hopefully you've learned a thing or two about databases today, because it's one of the most important pieces of software in this day and age. If you're a web developer, especially a back-end developer, you're using databases every single day, and yet most likely you don't actually know much about how they work internally. And that's what I find interesting about systems programming. When I was a new programmer, at some point I realized, hey, all the software that I'm using, from the operating system to the shell that interprets my commands to the pixels on screen, somebody had to write those. How did they do that? Because all I know is writing hello world in Python. And especially with databases, for some reason, all this time I thought that compiler programmers were like the gangsters, but man, everybody gangster till you gotta deal with low-level disk data structures that don't fit in RAM. So all my respect goes to those who have written Postgres, MySQL, SQLite, or any other serious database that we use daily, because it's extremely complicated. So if you're interested in databases or systems programming, because I'm pretty sure I must not be the only one in the entire world who's crazy enough to want to understand how this works, all the source code is available on GitHub. This project is meant to be a learning resource. So it's written in such a way that it's meant for reading and understanding how it works. Even though there are 25,000 lines here, half of that is probably just documentation, because I wrote like entire dissertations on how every single algorithm works. There are a lot of ASCII diagrams that make it easy to visualize what the algorithm is doing in each step. There are also over 270 different tests, which you can use to say, okay, this is supposed to do that, this is supposed to do that, so you can sort of figure it out. Now, I'm not saying that this codebase has any quality whatsoever. All the code in here is pretty much garbage. The performance is horrible, it's very unstable, so if you try it out, expect it to crash. What I'm saying is that it's easier to read and understand than some giant codebase like Postgres. If you enjoyed this kind of computer science content, then leave a like, subscribe, share the video, and do the YouTube algorithm stuff, because I have countless ideas for projects like this, and I'm not gonna be able to work on them unless you actually watch the videos. So do the YouTube stuff, and I'll see you on the next one.